All right, so just continuing looking into different ways of expressing and understanding complex numbers. Last time we were introduced to the phrase modulus or absolute. Well, absolute value is not new, but the modulus of a complex number we can think of as the length of the vector or the distance from the point to the origin. In this case, it's being represented by the variable r. And whereas the argument can be represented by an angle in standard position of this vector. And so using some basic trigonometry, if we know the modulus or the length of the vector, or in this case the hypotenuse of this right triangle, and we know the angle theta there, we can always use basic right angle trigonometry to figure out the base and height of this triangle. Or in this case, the base representing the x coordinate of this point and the height representing the y coordinate, which relates to how we express a complex number in Cartesian form. And so if we have a complex number described in this way, and so I have a complex number z in which we know its modulus or its absolute value is 8, and we know the argument is 5 pi over 6, we can write it into different forms. And so first, let's visualize this, which even if you're not asked to, I would always recommend. All right, so I will look at the argument first, 5 pi over 6. That is 5 times 30 degrees, or 150 degrees. So I can imagine some angle like this. And come back here. And we now know if the absolute value is 8, the distance from here to here is exactly 8. And so keep in mind the 150 degrees, or I'll keep it in radians, 5 pi over 6 was that angle from there to there. 8 is the length, the absolute value of that vector. All right, so in polar form, which is one of the new ways of expressing expressing a complex number, we can say z will equal, usually we'd start with a plus bi, where a is the x coordinate of this point here, and b being the y coordinate. Well, as was briefly mentioned earlier, that a is the same as 8 times the cosine of 5 pi over 6. Plus no, I'm correct. Never mind. I'm just tired. And so the b is the y coordinate here, which is going to be 8 times the sine of 5 pi over 6. And all of that times I. So that's it. This is one way of showing in polar form. A little more conventional, I should say, is if we take out the factor of 8 there, we have 8 times the cosine of 5 pi over 6 plus I times the sine of 5 pi over 6. Same thing though, just the 8 factored out. A little more conventional right here. That's when we write something in polar form, we always end up with the cosine of some angle plus I times the sine of that same angle. And so a more abbreviated way of writing this is just to focus on the CIS, cosine, imaginary unit sine. And so I can also write it like this, 8 CIS 5 pi over 6. And so just keep in mind that 5 pi over 6 represents, again, that angle in standard position. I just realized I wrote this wrong right here. I am very tired. It's a Monday morning. I apologize. And if you see something written in this form, you just need to understand it means one of these two. All right, we call that polar form. And all three of these are in polar form. If I want it in Cartesian form, I need to actually evaluate the cosine of 5 pi over 6 and the sine of 5 pi over 6. And so I want this in the Cartesian form. That's what we've seen before. Well, the cosine of 5 pi over 6 is negative root 3 over 2. And the sine of 5 pi over 6 is a half. And so in Cartesian form, we have z equaling 8 times, I'll go like this, minus root 3 over 2 plus 1/2 I. Really just taking what I had right here, putting that right there, and what I have right here, and putting that right there. If you want, since distributing the 8 is quite pleasant here, you get, if you distribute the 8, you get negative 4 root 3 plus 4i. Keep in mind as well, on your GDC, you should be able to just type this into your GDC, and it should give you a decimal approximation of this. It would be like negative 6.93 plus 4i. All right, the last form I want to talk about is Euler form, or Euler form, I should say. Bad me. Which is also based on just the argument and the modulus. And it can be written like this, where it's z equals, the modulus is always the coefficient 8 times e, Euler's constant, to the power of I times the argument, 5 pi over 6. And again, if you type this into your GDC, it should quickly put it into at least an approximate form of Cartesian form. Now, why, or a proof of how this here is equivalent to this, is beyond where we're at right now. So you don't need to be concerned about proving that how these are equivalent just at this time. We haven't learned enough to prove that. But in practice, notice these two forms, while they're different, they're pretty interchangeable in terms of they're both based on the argument and the modulus. All right, and that said, I have, for these two complex numbers, I want to write them in both polar form and Euler form. Again, the sort of new forms. And so even though it doesn't ask for a visual, I am going to visualize these as an Argand diagram. And 2 minus 3i, pretty easy to visualize. It's 2 comma negative 3, so I don't know, like right here, let's say. There's my vector. Which means the modulus, or the absolute value, is the length of this hypotenuse if I imagine a right triangle. Although, again, I don't always want to have to draw that. So the modulus of z1 is going to be root 13, 2 squared plus minus 3 squared, the square root of that. The argument, just do a little bit of trigonometry here. And we talked about this sort of stuff a lot before. So you should get approximately, I'm going to stick in radians. And by default, we tend to work in radians at this point. Negative 0.98279. And it goes on and on and on. And so, once I know the argument, and notice I should say the argument I know is negative because as an angle in standard position, we have to be looking that way. If we're thinking this way, and we have some positive angle getting closer to 2 pi. Again, by convention, we always stick, like mentioned last time, either from here to here or from here to here. So in this case, I need to have a negative argument. And so in polar form, we have z1 approximately equaling, I'll say root 13. Well, that's exact. The angle is approximate. Negative 0.9. I'll write it to 3 sig figs, 8, 3. So that being in polar form. In Euler form, same idea, root 13 times e to the power of that same angle, 0.983 times I. And keep in mind, if that angle was actually a special angle, then I could be more exact, but these are both approximations. All right, and then so for over here, I have 2i. So no real value for this, it's a purely imaginary number. So hopefully we can visualize this quite nicely. This means my vector is just going straight up. The coordinates would be 0, 2. And so in this case, the modulus I can see right away. The modulus must be 2, or the absolute value must be 2. And the argument is 90 degrees, or in radians, pi over 2. So these are exact. And so in polar form, I have z2 equaling exactly 2 cis, or you could write the longer form, pi over 2. Or I could write in Euler form equals 2 times e to the power of pi over 2i. All right. Lastly, I have two different numbers here, each written in Euler form. I want to write them in both polar and Cartesian form. So while I'll make a visual of each again, we don't necessarily have to. And hopefully we right away realize of these two forms we want to write in, polar form is going to be faster because it's pretty much everything we need has been given to us. Again, when you see something in Euler form or polar form, they are both based on the modulus and the argument. But that's it. It's always good to visualize these. So for e pi I, that means I probably want to look at the argument first, which is pi, which is from here to here, a distance of 4. That's pretty easy to visualize. So I have negative 4 comma 0 as my point. And so again, with polar form, I can say Z1 equals 4 CIS pi. I could have done that right away, but now that I visualize this, Cartesian form should be quite quick. Z1 is going to be my x-coordinate is negative 4 plus no I, so really just negative 4. And for this, same idea, I will visualize this, whether or not I need to do it or not. And I will always recommend, like I said, we visualize these as soon as you're dealing with a complex number. The argument is negative pi over 3, which is negative 60 degrees. So roughly like this. And 2 root 3, I should say, is the modulus. So 2 root 3 is the length of that. So again, I can, without even doing that, I can write this in polar form. In polar form, this is exactly 2 root 3 CIS negative pi over 3. To write this in Cartesian form, I need to actually evaluate what the x and y coordinates would be here, which is going to be 2 root 3 times the cosine of minus pi over 3 and 2 root 3 times the sine of minus pi over 3. And so I'll start with just the cosine of minus pi over 3 is exactly a half. It's in the fourth quadrant, and cosine is always positive in the fourth quadrant. The sine of minus pi over 3 is going to be negative root 3 over 2. Again, building on things from trigonometry earlier. And so put it in Cartesian form. It's going to be 2 root 3 times 1/2 for cosine, plus a negative, so just take away root 3 over 2 times I. Which, if I distribute the 2 root 3, we get exactly root 3 for the real part of our value minus just 3 whole for the imaginary coefficient.